How do you make an artificial intelligence model explain its decisions? This walkthrough focuses on implementing explanation tasks with widely used Python libraries, then judging the quality of those explanations and presenting the findings clearly. You will move from core tools to practical reporting in a single flow. Explanation tasks in artificial intelligence use Python libraries such as Lime, SHAP, and LO6 to make machine learning models more interpretable. These tools support debugging, compliance, and trust in artificial intelligence systems. The overall goal is to apply explanations to real-world datasets and evaluate how useful those explanations really are. Python offers several libraries for explainable artificial intelligence, each suited to different model types and use cases. These libraries help interpret, visualize, and explain predictions. They support trust and accountability by showing how a model reaches a result, rather than leaving the decision hidden inside the system. LIME stands for Local Interpretable Model Agnostic Explanations. Its purpose is to explain individual predictions by using surrogate models. It works with any model type and focuses on specific instances. A typical use case is explaining why a loan application was rejected for one applicant. SHAP stands for Shapley Additive Explanations. It provides feature importance for both global and local interpretability based on Shapley values and game theory. It can be used in model-agnostic and model-specific ways. A common example is showing how income or credit score affects loan approval decisions. ELI5 offers feature importance explanations for linear and tree-based models. It is known for quick and intuitive visualizations, including permutation-based feature importance. This makes it useful for debugging simpler models. One cited use case is identifying the strongest predictors in fraud detection data. The material also names other tools that support explanation-related work. AI Fairness 360 focuses on bias detection and mitigation alongside explanation tasks, with a use case in hiring algorithms. The What If tool is an interactive visualization tool for exploring predictions and testing how input features affect them. Library choice depends on the task, the model type, and the explanation needed. Lime is suited to instance-specific explanations. SHAP is suited to local and global feature importance, including complex models. ELI5 is best for linear and tree-based models, while fairness-focused tasks may call for AI Fairness 360. Best practice starts with understanding the model type. The material recommends SHAP or Lime for neural networks or black box models, and ELI5 for linear regression or tree-based models. It also advises matching the library to explanation needs, computational resources, fairness goals, and exploratory analysis requirements. For implementation, the dataset named is the UCI Adult Income Dataset, used to predict whether income is above $50,000. The preparation steps are to load the dataset, pre-process it, and then train a classification model. This creates the foundation for applying explanation techniques afterward. The example model is a random forest classifier for income classification. In the summary, this model is described as having high accuracy and the ability to handle complex relationships. At the same time, it may require parameter tuning for optimal performance. That balance matters before explanation methods are applied. Lime is applied when you want a local explanation for a specific prediction. Its role is to show why a single decision happened, such as a rejected loan application. The material describes Lime as intuitive and easy to interpret, but also computationally intensive for large datasets and sometimes unstable for similar inputs. SHAP explains global and local feature impact with robust theory, but high compute cost. SHAP is used for global interpretability and can also support local explanation. It analyses the overall importance of features and their impact on predictions. In the examples, SHAP shows which factors matter across a full data set. Its strengths are robust, theoretically grounded explanations, though the computational cost can be high. The three libraries differ in compatibility, explanation type, strengths, and weaknesses. LIME is model, agnostic, and local. SHAP is model agnostic and model specific, with both global and local explanations. LI5 is limited to linear and tree-based models and is strongest when you need quick feature importance visualization. The practical cases span healthcare, finance, and retail. In healthcare, SHAP is used to identify influential symptoms and tests for disease diagnosis predictions. In finance, LIME supports case-by-case loan explanations, while SHAP gives global insight. In retail, LI5 helps explain feature importance in recommendation models. Assess explanatory value. Explanations should not just exist, they should be assessed for quality. The material uses three metrics for this purpose: fidelity, interpretability, and stability. These measures help determine whether explanations are useful, reliable, and aligned with real-world applications rather than only looking persuasive on the surface. High fidelity supports trust in the explanation, but the material also warns that accuracy alone does not guarantee interpretability. Fidelity measures how well an explanation approximates the behavior of the original model. One example given is a LIME surrogate model closely matching the original model on test data. Interpretability asks how easily a human can understand the explanation. An example is a SHAP bar plot ranking feature contributions in a classification task. Stability checks consistency across similar inputs. SHAP is described as consistent across slight variations, while LIME may be less stable because it relies on local surrogate models. These profiles explain why each library suits different explanation tasks. Presenting findings begins with a clear report structure. The material lists an executive summary, methodology, findings, recommendations, and implications. The report should explain the chosen techniques, present explanation-backed insights, suggest actionable steps, and discuss ethical, legal, and operational impacts for stakeholders. Visual communication can include bar charts, heat maps, interactive dashboards, and SHAP force plots. In loan approval, SHAP summary plots highlight key predictors and LIME explains specific rejected applications. In healthcare diagnosis, SHAP identifies influential factors, while patient-specific LIME explanations support clinicians and local decision-making. 0203-0405. The communication examples show why presentation matters. In financial services, a SHAP bar chart on income and debt improved trust in the artificial intelligence system. In healthcare, SHAP force plots enhanced clinician confidence. In retail, heat maps improved stakeholder understanding of recommendation logic across different user segments. You have seen how explanation tasks can be implemented with libraries such as LIME, SHAP, and LI5, supported by fairness and visualization tools where needed. You have also seen how to build a simple model, evaluate explanation quality through fidelity, interpretability, and stability, and present findings clearly. That combination supports transparency, trust, and better decision-making in artificial intelligence.